Here we go. All right, so pressure is force divided by an area. What is the SI unit for pressure? Okay, capital P, little a. Okay. What if we had, what does Pascal equal to? Over? Very good, yes, Sydney. If you forget that, look at the formula. What is the SI unit for force? Newton. What's the SI unit for area? Because it's what? Length times width. Meter times meter. Get it? Okay. So what if we had, let me think for a second here. What if we had a pressure of 500 newtons per meter squared? How many Pascal is that? What, Ethan?
I didn't mean to say that.
Are you just saying stuff to be talking?
No, I was.
Okay, you were really, okay, so you changed your mind? Okay, Kay? Do you want to justify that? Or can you explain that? That's what I mean to justify.
Because Newton and Pascal are the same?
Yeah, trick question. A Newton per meter squared is a Pascal, so it is, okay, y'all good with it? Okay. What is the pressure at sea level? Zero. Sea level, the air pressure is 1 what?
1,000?
No. Air pressure, remember when we did the collapsing can and we talked about air pressure? At sea level, it is 1 ATM. Does anybody remember what ATM stands for? Alex? Atmosphere. So, the relationship between atmosphere and Pascal, 1 atmosphere is equal to 101,325 Pascal. So right now, our air pressure is 1 atmosphere, or it's 101,000 Pascal. So what does that mean about a Pascal? How big is a Pascal? It's small. It's not very much at all, right? Okay, so what about this pressure right here? This 500 Pascal? How many atmospheres would that be? Can we do a conversion? Okay. Are y'all doing this in algebra? We did it a few months ago. Put that over 1, multiply by unit multiplier. What unit we want to get rid of? Pascal. What do we want to change it to?
Atmosphere.
What's the relationship? 1 atmosphere is, let's just round that to 101,000. Okay? So what do we do? Multiply or divide? Anybody got a calculator? Don't come up to get them. We don't have time. So you're going to divide 500 divided by 101,000. And we get, anybody punching it in? Nobody's punching it in?
500 divided by 101,000.
Uh-huh.
0.0049.
Good. Very good, Ethan. How many sig figs?
Third.
The way I have it written.
1.
1. Why is it 1? No decimal. So when we say 0.00495, what should we round it to?
0.0045.
And don't forget your unit. Okay, so that is a really low pressure. This pressure is lower than atmospheric pressure. Way, way lower, right? Okay, any questions about pressure or units of pressure? All right, moving on. Pascal's principle. Change in pressure. Of a fluid is transmitted how?
Equally in all directions.
Okay, so what is a fluid, by the way?
Something that can take shape and any volume.
Okay, it can take on the shape of the container, has a, okay, not necessarily volume, but takes on the shape of the container, right? So what states of matter are fluids? Gases and liquids. Now, hydraulics. Hydraulics use Pascal's principle. So like on a dump truck, that hydraulic lift that's on the back of it uses this science. So what kind of fluid does it use in the piston?
Hydraulic fluid.
Hydraulic fluid, is it a liquid or a gas?
Liquid.
It's a liquid, so why does it use liquid?
Definite volume.
Definite volume, very good. You don't want the volume to change. Okay, so let's take a look at a hydraulic lift or hydraulic piston. Okay, remember you have force over area, right? This is in, this would be the input, this would be the output, right? All right, now we're going to put a change in the pressure. So we're going to put in a force here, and we're going to change the pressure in here. Okay? Listen to me carefully. How does the pressure here compare to the pressure here? Careful. What am I asking about? What am I? Yeah, why, Alexis?
The pressure is transmitted equally and unchanged.
Another trick question. Be on your toes. Pay attention to the wording. The pressure here is equal to the pressure here because that pressure is transmitted equally throughout this. Pascal's principle. If all this, now what y'all were thinking about is what I said the other day. If this is F1 over area 1 and this is F2 over area 2, how does F1 compare to F2? Lower. In other words, you get a big output of force. My bad. You get a big output of force for a small input. That's what you guys were thinking about. You were thinking about what I said the other day. But what if I ask about the pressure? They're equal. Y'all good? You see the difference? Any questions about Pascal's principle? Okay. Bernoulli's principle. Bernoulli's principle, they just demonstrated back here. As fluid speed increases, what does pressure do? Pressure decreases. Okay? So, we talked about the airplane wing, right? We got low pressure here. No, my bad. My bad. Okay, airspeed is faster here, right? Airspeed here is slower, right? Wake him up. Okay, so where's the low pressure? Huh?
Way on top.
On top. You got low pressure here, what we got here, and everything, force always goes from what to what? Is the force gonna push this way or that way?
Press up.
Press up from high to low pressure, right? What do we call this force?
Lift.
So if you build an airplane with the curved side down, you gonna sell any of those airplanes? No. It's gotta be on, that's why it's gotta be on top. Curved side's gotta be on top, right? Okay. Any questions about Bernoulli? All right, let's wrap this thing up. Archimedes. Whoa, that's a strange name. What does it sound like to you?
Sounds like a,
Greek philosopher.
Have you been reading?
like some type of math company.
Yes, this was an ancient Greek philosopher, Archimedes. Every time you go swimming, you experience Archimedes' principle. Here's Archimedes' principle. It deals with something called buoyant force. You've heard of buoyancy, haven't you? What does that mean? Just in general, just everyday life. Come on, y'all. Yeah, fluid pushes up so that you can float. Yeah, that's all it is. Right, Jasmine? Okay, here's what Archimedes found. Buoyant force is equal to, let me write it this way, is equal to the weight of the displaced fluid. I can't spell. What does the word displaced mean? Kind of, sort of, yeah. You are displacing air right now.
You're taking its place.
You're taking its place. Yeah, you're taking its place. You're pushing air out of the way, right? You move over here, what fills in right there?
Air.
Air. What did you push out of the way here? Air. You're displacing a fluid. Okay, when you're in water, you're displacing that fluid, right? However much fluid you displace, you get its weight. What is weight again?
Gravity.
Gravity. Gravity pulling on it, right? However much that water weighs, that's how much force is pushing up on you. So what is buoyant force dependent on?
Weight.
Well, if that's true, how do these big steel ships float?
Under shape.
Close. You're real close. Huh? You're real close. Okay. How much water? Okay. If you displace a little bit of water, what kind of buoyant force you gonna have?
Not that great.
Little. You displace a lot of water,
You're gonna have more.
you're gonna have a bigger buoyant force. So what is it really? I mean, yes, density plays into it, but what really is the difference?
How much fluid?
How much? So what is that?
Mass.
Volume. Awesome. It's dependent on the volume of the water displaced. So that's why they're very careful on the shape. If you take two objects of the same mass, and one is taking up a bigger space than the other, which one's going to float? The one with the bigger space. I'm trying to think of an example right now, and I just can't. But I've got a demo for you that we'll do in just a second. Any questions about that? Okay, that is the end of chapter 13. I don't know if I can start it again. I don't think I can.
Yeah, it's recording.
It's recording. Okay, one last thing. Let's go back to just pressure in general. I got a beaker of water. Where is the pressure greatest?
In the water.
In the bottom.
And why is it pressure the greatest in the bottom?
More water.
You got all this water on it, right? Force over area, and this, remember when I made you stand on one toe? Right? Okay, what if I made you hold a box of bricks?
There's a lot more pressure.
How come?
There's more weight.
More weight. Okay, so what if we pour some more water in here? What happens to the pressure at the bottom? It's greater. Y'all good with that? Because you got more weight, you got more force, right? Okay. I think y'all are ready. Hold on, one more question. Let's talk about density. Density. Density is mass over volume, right? If we have water in one beaker, which is going to float in it? Something that is, let's say density of water is 1 gram per cubic centimeter. And we drop a piece of iron, and we drop a piece of cork in that water. Which one's going to float?
Cork.
Why the cork?
That's less dense.
Less dense. So if an object is less dense, or at least equal to or less than the density of the fluid, it's going to float. Why won't the iron float?
It's got more weight.
More dense. If it's more dense, what's it going to do? Sink. Now you're ready for the test. Any questions?
No.
All right, I will put this video on that channel if you choose to watch it tonight.
When